Welcome to Central High School's IB Physics Unit 3. I am Mr. Tompkins, and we are going to discuss how gases behave when their temperatures change. The kinetic model of an ideal gas is the third lesson in thermal physics. In this lesson, we will determine how a gas behaves under different pressures and temperatures. Here are the objectives that we will cover in this lesson. You will receive a copy of these on your checklist, and you may peruse them at your leisure at that time. What is an ideal gas? An ideal gas is one that follows these assumptions. The molecules of the gas are perfect elastic, which means they don't lose any kinetic energy when they collide. The molecules are spheres. The molecules are identical. There are no forces between the molecules. This means they have a constant velocity between collisions. The molecule's total volume is much smaller than the total volume of the gas, which means the molecules are very, very tiny. These assumptions are not true for all gases, but using them we can predict some very important things about the gas. Some gases turn into liquids under certain conditions, such as higher pressure or lower temperatures. The pressure, volume, and temperature can be attained by using this model. When are gases not ideal? In this first video, a gentleman pours carbon dioxide out of a cup onto a lit candle. Because of the pressure of the atmosphere on the gas, it behaves like a liquid, seen by the fact that it can be poured. In an environment that is devoid of air, carbon dioxide acts as an ideal gas. In this second video, we see nitrogen that has been cooled until it reaches its liquid state. Because of its temperatures, there are now forces that act between the molecules. This creates a point where the gas is no longer ideal. But for temperatures higher than its freezing point, nitrogen acts like an ideal gas. We learned in the first lesson of this unit that greater temperatures relate to greater average kinetic energy, and thusly to greater velocities of the substance's molecules. In the ideal gas model, we assume that all the molecules are traveling with the same kinetic energy, but in reality they are traveling at many different velocities. Notice how in reality some molecules have greater velocities or temperatures than the others. What is pressure? Pressure is a result of our particle model following Newton's three laws. Just to review, Newton's first law states an object at rest stays at rest, and an object in motion maintains a constant velocity unless an unbalanced force acts on it. Newton's second law, the change in an object's momentum is proportional to the force on that object. And Newton's third law, for every action force, there is a reaction force that is equal in magnitude but opposite in direction. In this animation, I have a molecule in motion. It maintains a constant velocity until it collides with the side of the container. This is Newton's first law. The object's momentum changes when it impacts the side of the container. Notice the change in the velocity vectors. They have the same magnitude but are in different directions now. This means there is a force from the container on the molecule, which is Newton's second law, and it's represented by the blue arrow. That's the force. If there is a force on the molecule from the container, then there must be a force on the container from the molecule that is equal in magnitude but opposite in direction. And this is Newton's third law. So now we have a force on the outside of the container, and that is what we use to define pressure. This was an example of only one molecule. Now imagine billions and billions of these molecules colliding on the surface of a container. Instead of a force only at one time and location, these forces are all over the surface at all times. So pressure is defined as the amount of force over the area of the container that holds the gas. And so pressure equals force divided by area. And here are the variables: P for pressure, capital P for pressure, capital F for force, and capital A for area. Pressure is measured in atmospheres, pounds per square inch, or in this class we will be using the Pascal. 1 Pascal equals 1 Newton per meter squared. There are two ways that we can alter a pressure in a container. In order to do this, we must reduce the force between the gas and the container, or reduce the amount of times that force occurs. We can change the volume of the container. This changes the amount of time these forces occur. Here I have some gas trapped in a container. Notice the pressure gauge to the right and the thermometer on the top. If I increase the volume of the container, we see that the pressure gauge decreases. This is because the molecules are allowed to become spread out and they do not impact the sides as often. As I decrease the volume, the pressure increases. This is because those collisions are taking place more often. Because of this, we can say that pressure is inversely proportional to volume. Another way we can affect pressure of a gas in a container is to change the temperature. This changes the amount of force on the container from the gas. Now notice as I increase the temperature of the gas trapped inside my container, the pressure increases due to increase in the change in momentum of the molecules in the gas. As I decrease the temperature, the change in momentum is less than before, and the subsequent pressure is also less. We can now say that pressure is proportional to the temperature of the gas. This brings me to the next slide, the ideal gas law. Now, the ideal gas law states that the number of moles of a gas times the universal gas constant times the temperature of that gas divided by the gas's volume equals the pressure that that gas exerts on its container. If we put it in an equation forwards, we get P for pressure equals N capital R capital T divided by V. The universal gas constant, which is capital R, equals 8.31 joules per mole Kelvin. Because the number of moles and the universal gas constant are the same for a given amount of gas, we can rearrange the equation as such. This equation is useful for finding initial and final pressures, volumes, and temperatures for a gas that undergoes a change. So ideal gas example 1. I blow a balloon up outside. The temperature of the balloon is 313 Kelvin, and the pressure outside today is 110 kilopascals. If the balloon's volume is 1.5 liters, how many moles of air did I blow into the balloon? Some things we need to notice. A balloon increases in size because it must equalize the pressure inside to the pressure outside. If it is not able to do this, then the balloon will pop. Our pressure is in kilopascals, so we need to convert that to pascals, and our volume is in liters. We need this to be converted into cubic meters. And there we go, I've done my conversions. You can look at these conversion factors online or in your book. The next step is to pick out our equation. We're going to use pressure equals the number of moles times the universal gas constant times the temperature and divided by the volume. We will rearrange to solve for the number of moles, plug in our knowns, and calculate, so that we get the number of moles that was breathed into the balloon, or blown into the balloon, is 0.063 moles. So working with gases. One of the gases do work on objects. Some good examples that we have is, one of the most common examples of work done by expanding gases is in your automobile. Right? The work is done by rapid increase in temperature of the fuel-air mixture caused by the spark plug. This increase in temperature corresponds to a rapid increase in volume, which pushes the piston back down. So let me narrate the video for you. Here we have a combustion engine. Right? It has all the labels there if you want to pause it so that you know what they are. Pause it now. All right? The first stroke of a combustion engine is called the intake stroke. And during this time, fuel and air are sucked into the cylinder by the piston. Right? So notice we're getting gases inside our engine. On the compression stroke, the next stroke, we seal the cylinder off and we compress the gas. So now we're changing the volume of the gas, which increases the temperature of the gas, the fuel-air mixture. And then when we have it completely compressed, we ignite the fuel using the spark plug, which further increases that temperature. Now that increase in temperature causes what's called the expansion or the power stroke. So now the volume is changing rapidly due to that rapid change in temperature, and that pushes the piston back down. After this, well, all we have left to do is to get rid of the expended fuel air gases, and that goes out on the exhaust stroke. And then your engine repeats itself over and over again. And it does this thousands of times a second. Thousands of times a minute, I mean. So here I have another example problem. The compression stroke of an automobile engine piston compresses the air-fuel mixture inside the cylinder from an initial volume of 0.0004 cubic meters to 0.0002 cubic meters. Assume the pressure of the air-fuel mixture at the beginning of the stroke was 1.10 times 10 to the 5th pascals, and at the end of the stroke is 6.9 times 10 to the 5th pascals. If the mixture started at a temperature of 288 Kelvin, what is the final temperature of the mixture? So we're talking about the compression strokes. We want to know how much does the temperature increase throughout that compression stroke. So I'm going to take the second equation I gave earlier, the one that we rearranged so that we can figure out changes, and I'm going to solve for the final temperature of the gas. All I have to do now is plug in my knowns from my word problem and then calculate. So I get that the final temperature of the gas is now 900 Kelvin. So the gas went up from 288 Kelvin, which is right around 75 degrees, somewhere around in there. I wouldn't even say that much. 25 degrees room temperature, 70, yeah, something like that. Up to 900 Kelvin, which is a lot. So here's some more examples of working with gases. Explosions are caused by rapidly expanding gases also.
Please hold on to the glass of water.
Okay.
So if you take a glass of water and you just drop Alka-Seltzer, for example, into the glass of water, you get this great bubbling reaction. And it's actually a great way to be able to teach chemistry because it's creating carbon dioxide. So if you could trap that carbon dioxide, totally fun. All right? So here's what I want you to do. This is an antique. It's called a film canister. A long time ago, they used to have film in a camera.
I've read about it.
Yes. And so here's what you do. You put a little bit of water. It's a classic. You put a little water in the film canister, and then you drop the Alka-Seltzer tablet in, and then you just put the lid on. So you and I are going to do this together. I'll be the lid person.
Okay.
You're going to be the Alka-Seltzer person, okay?
Okay.
So these have a little bit of water in them, and here's your Alka-Seltzer tablets.
Okay.
And so you're going to start from
How many
over here.
Alka-Seltzer am I putting
Just
in?
one.
Oh, just one.
So like put one on, and
Okay.
then, yeah, and now I'm going to put the lid on.
Okay.
Now you do the same thing again. You're going to want to go pretty fast.
Okay.
Keep going. Keep going. Good. Keep going. Good. Oh, wrong one. Okay,
Yeah.
sorry. So good here, like this, and this one's. So sorry. So there's a little bit of. Yeah, don't worry about that. It's fine. So what's fun is you turn them upside down like this. For see. Is that awesome?
Yeah.
Yeah. But that took us a lot of work because it was fast. So my good friend, a guy by the name of Science Bob, said, if you take the Alka-Seltzer tablet and you glue it to the top here like this, then you put the water down below, and then you can turn it over, and it's like a time bomb. So here's what I did. I just put magnets on them like this, and so now watch. I've got 50 of them here. So, all right. So now it's ready to go. Isn't that awesome?
Yeah.
All right. So now, this is where you come in. You're going to hold on to this.
No, I'm not. No.
Of all these times I've been on, this is a no, I'm not?
No, I'm not.
It's fine. I am.
All right.
All right. So watch this. So you turn it over like this, and you see there's a reaction going on in here.
Right.
No, it's fine. It's not. And sometimes you'll see just a little fizzing going on, and sometimes you can hear like a little bit of popping, but you can hear the fizzing kind of taking place inside. Sometimes it takes longer than others,
Yep.
but you'll see a little.
Sometimes it takes.
This is yes. So this is where I see it's like a time delay. It's like a time reaction. That's fun.
Yeah.
Sorry.
My eye!
Sorry. You okay?
Yeah.
Okay. That's dumb.
A lot of people work here, you know.
That was not very smart.
All right.
But then I was thinking, if you could do this in a classroom and make it bigger, it'd be fun. So if you don't mind, come here and take a look at this.
Yeah.
Right? Just be careful of
Oh, I
this.
see it already.
So here's what I have. Yes, put that on, please. So this is what this is going to look like. There are 3,000 film canisters under here, all prepared with Alka-Seltzer tablets.
Have you tested this?
Never.
No, seriously, have you tested it?
No. We did 200 in rehearsal.
And this is how many?
3,000. Because you always say, go big, right?
I do.
And if you're going to get kids excited about science,
Yep.
this is how you're going to do it.
Okay.
So here's what you and I are going to do. We're going to start with this one. We're going to tip it over. Then we're going to tip this one over. And then we're going to stand here and enjoy.
All right.
Got it?
Yep.
All right, come
What
over
about
here.
these people?
No,
What-
they're fine. They're
All right.
fine.
All right.
These are fine. All right, you ready?
Yeah.
All right. So you get on this end over here.
Uh-huh.
We're going to just flip it over. Ready? 1, 2, 3. Flip it over. Good. Good. Okay, now come over here with me. All right. Flip this over. Okay, here it goes. All right. Good. Nice. All right. Now, this is what's good about this. Is that these are just going to, oopsie, we should do this. We should I've never actually done this many before. That looks pretty good. What do you think? It's done. Ta-da.
Wow.
I think that's fun.
That's amazing.
I like that.
That was so fun.
I will never do that again in my life, but I
No.
love that.
Oh, man. This is a big cleanup now.
Oopsie.
Okay, so the work required to lift the space shuttle off the ground is due to the increase in temperature of the gases that are expelled from the thrusters. So once again, this is a more practical use of the work done for gas besides exploding film canisters. And so we'll go ahead and watch this video of the space shuttle being pushed off. And what you're going to see is that the only force on the space shuttle that is pushing it up is the gases from the boosters or from the thrusters below it. And there we go. Exciting. But without this ideal gas law, we could never make it to space. Absolute zero and the Kelvin scale. If we look at a graph of an ideal gas's pressure versus temperature, we notice that there is a trend. And so here I've done an experiment where I've taken an ideal gas and I've looked at the pressure over the temperature of the gas, or as I heated up the gas, I noticed how the pressure rose. There should be a point where the temperature is so low that the pressure on a container holding an ideal gas should be zero. Okay, we can see that by looking at the trend line. All right, which means that at a point where the molecules of the gases are not bouncing off the sides of the container, or they have zero kinetic energy. In other words, the molecules are stationary, they're not moving. This temperature is negative 273 degrees Celsius, and it's called absolute zero or the 0 Kelvin. And this is why we use the Kelvin scale when we discuss ideal gases, is because there is this temperature in Kelvin where all motion of molecules ceases to exist, where the molecules are completely stationary. And this ends lesson 3 of thermal physics, the kinetic model of an ideal gas.